BigML's acclaimed UI makes powerful machine learning easy and intuitive. But underneath the UI is a fully featured REST API, which can be used to make scalable predictive apps in the cloud. To understand how important that we think a solid API is, let's take a high-level look at the BigML architecture. From this so-called 10,000-foot view, there are three major components. At the top is what we call Sky. This is our front end or main UI that you see at bigml.com. Below that is what we call our Appian layer, which provides our API and is available at bigml.io. And the bottom layer, which we call Wintermute, is our back-end computation layer where we implement our machine learning algorithms. Now, this is not just a picture. This is the way our infrastructure is actually implemented. When we want to bring a new feature, our back-end team develops it in the Wintermute layer first. Our API team then integrates the new feature into our API. And then finally, our front-end team integrates the new feature into the UI using the same API that we expose publicly. Theoretically, a third party could write their own Sky on top of the BigML API. So let's take a closer look at how to work with the BigML API. First, just a quick comment about the agenda so you can kind of see what's coming up. I'm going to give a breakdown of the API, and I'll do a quick demo just using curl to directly interface with the REST API. Then we're going to talk about do a demonstration of a predictive application, specifically using JavaScript to make predictions. Then we're going to review some of the API bindings that are available. And after an introduction to the bindings, I'm going to show you a programmatic machine learning example of extending the BigML algorithm set using the Python bindings. And then finally at the end, if there's time, I'll make at least a brief introduction to our command line tool called BigMLer, which is another layer on top of the Python bindings. As you can see, we're going right from a basic introduction to our API all the way up to a more complicated example. So hopefully there should be something in here for everyone. So the base URL for the BigML API is https://bigml.io. This path is followed by optional elements that specify the API version and whether the call is to development or production mode. Note that the API is versioned using names, the current name being Andromeda. If these optional parameters are omitted, the default is to use the latest API version in production mode. And the idea here is that if we ever get to a point where we need to introduce a new version of our API that isn't backwards compatible, we'll add a new name, and you'll still be able to access the old version using Andromeda. If you're not worried about backwards compatibility, you can always omit that and get the latest version. After that is the resource type, which directly maps to the resources available that you see in the UI. That is source, dataset, model, evaluation, etc. And if the resource is being fetched, updated, or deleted, then the unique resource ID is required. And finally, the authentication, consisting of a username and an API key, is specified in the URL parameters. And note that the API key can also be an alternative key, which allows specifying granular permissions for each resource type and action. These keys can be managed in your account settings, which I'll show you real quick. So when you're logged in, if you click on your username, you can access this API key, and you can see this is your master API key. And I know it says keep it secret. Don't worry, I'm going to recycle these at the end of the demo. But you can also create these alternative keys, where here you can see I've given this key permission only to create predictions. And so I would use the same username in my API authentication. Oh, actually, I've extended it. But you can create new keys and assign very specific permissions to that key. And now you can use, for example, a predictive app where you only want to be able to make predictions. You can assign that specific permission. All right, a little overview of the methods. So the BigML API uses the standard post, get, put, and delete HTTP methods to create, retrieve, update, and delete resources respectively. Each API request may also contain configuration parameters, which are specified using JSON in the request body. the API response is also JSON formatted. Now, the only exception to this is when creating a source from a local file, in which case the body is multi-part form data. So let's go ahead and run through a quick demo just using curl and accessing the API directly. All right. Ooh. All right, so we'll start by configuring our username and the API key that we want to use in our environment. And we do this mostly as a convenience, because what we can do here is now we can define this authentication variable BigML auth that specifies both the username and API key settings in a URL parameter friendly format. And this makes it easy in scripts, etc., to just add that authentication. Also, our bindings use these same variables so that you don't have to have the authentication in your script. So now the first thing we're going to do is create a source. And so we'll do this by issuing curl with a post command. And we'll post to the source endpoint. And we need to add our authentication to that URL. And we need to let curl know that this is going to be a JSON content. And then we're going to add a little JSON document that specifies the remote parameter. And in this case, we're using a source file that's located in an S3 bucket. And additionally, we're adding a name parameter to this source, which we're calling a curl demo iris from S3. And we're going to run the output of that curl command, which remember is going to be a JSON document that comes back through this handy command line tool called JQ, which will pretty print the JSON for us. So let's have a look at that output. Okay, so we can see here this JSON document that came back. In particular, you notice that each resource that's created in BigML is assigned a unique identifier. It's formatted with the resource type, a /, and the resource ID. You'll also notice that there's a status field in this return, and that there's a code of 1. These codes actually have 3 negative values that indicate different types of failure or not runnable, and 1 through 5, 5 being that the resource is completely ready and available for use. And so in this case, we can see this is an example of the fact that all of these requests for making to BigML to the API are asynchronous. So I've asked it to create this source. It immediately returned this JSON document containing the identifier and a note that it's going to process this soon. So we'd like to actually try fetching this resource. So we'll issue another curl command with a get this time, and again to the source endpoint. But now we need to add the source identifier that we just received, and again our authentication, and of course run it through JQ again. And now we can see that this response is a little different, and this is because BigML has actually processed this source. It's taken a peek at the file. It's assigned column identifiers to each of the fields. It's auto-typed, so we can see here these columns are all numeric. And it has also, let's see, added an MD5 and some other information. So I was going to show, oh yes, here's all of the missing tokens. And of course, we could actually issue an update if we, for example, wanted to change this op type from numeric to categorical. We could actually do an update and pass in a JSON document specifying that field 000 should be categorical instead. But let's go ahead and create a data set from this source. So this time we're going to issue a post again, this time to the dataset endpoint, adding our authentication. Again, it's JSON. And this time the JSON document that we'll post in the body contains the key for the source that we want to create the data set from. In this case, this is the source identifier that we've created above. And again, the name. And we'll run this output through JQ again. And once again, we have a JSON document. We can see there's a unique identifier assigned to this data set. And again, in the status, it's code 1 being processed. So let's go ahead and fetch this data set. This is the new identifier. And we asked JQ just to tell us the status so we can make sure it's ready. And in fact, the data set has been created, code 5. So let's go ahead and use it to make a model. Now this data set is well formed, so I don't need to specify which feature I want to use as the objective. We can take BigML's default of using the last column. So I'll post to the model endpoint with my authentication, JSON, and in the document I'll specify this dataset identifier that we've just created. And now we have a new document that specifies this model, and again, there's a unique identifier. Now this model builds pretty quick, so I won't bother to check the status. I'm relatively confident it's done. Although if it isn't, we'll get a nice error message, so that'll be fun too. But let's go ahead and use this model to create a prediction. So now we'll post to the prediction endpoint, again with our authentication, again using JSON, and this time passing a document that specifies the model we want to use for the prediction and the input data we want to use. In this case, I'm going to input a value of 4.3 for the column identifier that's all zeros. And we'll run this output through JQ again. And now this, you'll notice that this initial response came back as prediction has been created and status code 5. So these one-off predictions are the only API feature BigML that are actually synchronous. So when you ask for one prediction, it actually generates a prediction and returns it in the initial response. And we can actually see the output up here. This is the predicted outcome, which in this case, this is the famous Fisher iris dataset. So the prediction is iris virginica, and there's a confidence in here as well. In this case, the confidence is 0.26. And we can also see the other thing is that this object contains all of the history, so you can still see all of the fields that were in here. You can see the data set that was used to create the model and the source that was used to create that data set, and of course the objective summary. So there's quite a lot of information in that object. Now you'll also notice that all of those actions that we've just taken through the API will show up on our dashboard. So here's the source I created. Here's the data set I created from that source, the model, and the prediction. This, of course, is because the UI sits on top of the API, and they see the same resources. In fact, it's easy to switch between the UI and the API using the API link button at the top of the screen. So anytime you're hovering over one of these resources, for example, this model, I can actually click this little gear icon here, and I can see a summary of the authentication variables, as well as a full URL to the API. So this is BigML.io to the endpoint, and the resource identifier and the authentication. And if I click on that, I can actually access this object, again, the same way we did through the command line, but now in my browser as well from the UI. So now that we've seen how to interact with the BigML API directly, we can run through an example of how a real-time predictive application might work. So let's imagine that we have a website which sells cars, and that we'd like to customize the appearance of the landing page by predicting what color of car each user might prefer and showing listings in that color first. So when a new user first connects, we have limited information about them. For the sake of simplicity, let's assume that it's reasonable to correlate the choice of browser and operating system with a car color preference. So this slide is kind of showing you an overview. Here we have the user agent is Chrome. We're predicting a yellow car. Here the user agent is Opera. We're predicting a green car. Now here's a high-level overview of how the complete application might work. So we have a web server, and it's writing logs, which contain, among other information, the browser user agent and the color choice that each past customer has indicated, perhaps in an inventory search. On a regular schedule, we parse these logs and upload them to BigML to create a model. When a new user connects to the website, we use the user agent information to generate a car color preference prediction in real time, and then deliver a custom experience to this user. So here's how the log data might look. Now we could actually parse this user agent data that you see on the left-hand side of this table, simply using BigML's text analysis feature. However, it turns out that there's some hidden information that can be deciphered from these strings, and it is possible using readily available libraries to extract extended information about the OS, browser type, and version, and often even the device the browser is running on, whether it be an iPad or Android phone, for example. If we use such a library, then the data might look more like this. So now we have browser version OS, OS version device, and then the color preference that we want to predict. Now, of course, we'll need to do this same user agent transformation during the prediction step. Now, from this data, it's trivial to build a predictive model using BigML. And now all that remains is to create the real-time piece, for which we will use JavaScript. And I'm actually going to show you all this code live. This snippet is just so I can kind of give you a feel for what's going on. So the basic idea here is as follows. Once the page has been rendered, the jQuery document ready event will trigger this function in the middle here. And what happens down here at the bottom is we use the UA parser to parse the user agent of the browser. We use the results of the parser to generate this agent object, which has all of the data in it, the browser name, browser version, OS name, etc. And then we call the create prediction. And all we do here is we build a dictionary with the input data. And then we use a simple jQuery AJAX call to the prediction endpoint, adding our credentials, type as a post, and we pass in the data in a JSON format, and what we get back is a prediction. So we can actually see this in action and examine the code live using a blocks.org site. And let me share the link to that and pull it up here as well. Let's see where to go. Here we are. So if I refresh this page, we can actually see it's detected that my user agent is Chrome, and it's making a prediction of a yellow car with a confidence of 46%. And I actually have a little user agent client that allows me to change my user agent, but it doesn't work in presentation mode for some reason. So let me drop out of there. And I can change my browser so that it claims to be Opera. And now we can see it's detected, this detects my browser as being Opera and is predicting a green car. And if I switch this to, say, Android, then it's predicting this little red coupe. Oop. Let me not leave this in Android. That'll probably mess up the rest of the presentation. Hang on. All right. So you should be able to find the link in the GoToMeeting client, and you can actually go ahead and click on that and try it for yourself. And of course, we have all of the code that we used to generate. There's all of the CSS we did to render, and here's the actual JavaScript as well. And that UA parser is easily findable on the internet. All right, so although it is possible to interact with the BigML directly, API directly, as we've demonstrated using curl and JavaScript, it can become tedious. Always building the URL, adding the authentication, building the JSON. For more complicated examples, it's easier to use a language-specific binding. So here is some of the languages for which bindings are currently available. You can find the full list, plus links to all of the bindings, documentation, and even a link to our online chat room at bigml.com/developers. Now, some of these bindings are maintained by BigML, and others by the BigML community. Now, since we use a lot of Python at BigML, it is typically the most up-to-date of the bindings, and is the one we will focus on in this presentation. Now, the main difference between using the bindings over direct API calls is that we now have an object with methods for each API action. So here's a summary comparing HTTP methods to binding methods. So similar to the table we had before, we have a create operation, which in HTTP was a post. And instead, we're going to have now this API object that'll have a create resource, and we'll be able to specify what we want to create the resource from, and some additional options specified in a document. And this funny little notation here is just meant to denote that there's a separate method for each type of resource. So you might have API create source, API create dataset, API create model, etc. Similarly, for a get, you can also do a get resource or even a list resource. To update, you can do an API update call, and to delete, an API delete. So let's actually do a quick demonstration of this. So the first thing I need to do is I need to load the BigML module. And I need to instantiate a connection to the API. Now you can actually, in that call I just did, you can actually pass a username and credentials, but I have them loaded in my environment. So it's using the default environment variables. Now, just like before, we want to go ahead and create a source. So we'll just call API create source, and we can pass in an S3 URL. And we can also pass in a dictionary with optional parameters. In this case, we'll assign a name of Python demo. And just like before, we can see here that this is now a document that contains information about this source that we just created, including a unique identifier. So we can use that or actually we don't even have to use the identifier now because we can create our data set. Oh, remembering that all of the create methods are asynchronous, we need a way to make sure that this resource is done. So the API provides an OK function, and I can actually just pass in this source object or source record that I just created. And what's going to happen is it will actually fetch that resource, make sure that it's either completed or failed, so it's attained some kind of a final state, and then it'll return true or false depending on whether it succeeded or failed. But that'll actually make the Python block until that resource is done, which makes it safe to go ahead and create a data set from it. So we'll create a data set from the source, and again, we'll name it Python demo. And again, we want to make sure that it's done. All right, and once again, as before, we'll create a model. Create model from the data set, passing in the name again, Python demo. And finally, we'll make a prediction. From the model, and now we want to pass in input data, which is its own record. Whoop. Got to actually spell it right. Sorry, guys. And we can see inside this object, I forget, output. Oh, here's confidence. And the prediction outcome is in here too. I've just forgotten where. A little mental block, sorry. Anyways, the other thing I want to show is that when we created this prediction now, it's important to understand that what happened is we actually passed a request to the API asking it to use this model identifier and this little JSON data that we passed. And that request went to BigML, and the prediction was created, and then the response was returned to us. Now, it's actually possible to use the bindings to create a local prediction as well. And the difference here is I can import this model object, and I can create a local model now instead of a remote one, just using the model object that we've created above. And what's going to happen is I'm actually going to fetch the model from BigML, and I'm going to instantiate it locally in memory. And I can now use this local model object to create predictions the same way as before, but now I don't have to sorry guys. There we go. I don't have to make an API call. These predictions are now happening in my local machine. And this is, of course, is one of the major advantages to the BigML platform, is that we don't restrict the models to we don't require you to use our interface to make predictions. You can extract your models in an actionable format and then use them to make predictions in your own infrastructure. All right, so as you can see, the bindings make it possible to seamlessly integrate local programming with BigML's machine learning algorithms in the cloud. So now consider this. Although BigML models and ensembles with bagging or random decision forests are very powerful, what if you wanted to extend BigML's capabilities with your own learning algorithm? So for this next demonstration, we're going to consider a boosting example. All right, well, before we can do that, what is boosting? So the basic idea is to combine multiple weak models into a more powerful classifier. BigML doesn't currently offer a boosting algorithm, but it is possible to use our API in a programmatic way to extend the learning capabilities of BigML. Now, while it is possible to correctly implement a boosting algorithm like AdaBoost or perhaps gradient boosting using the BigML API, I want to keep the demonstration simple to allow us to focus on how to use the Python bindings. So I'm going to implement an algorithm somewhat related to AdaBoost, which I'll call ToyBoost. So here's an overview of how ToyBoost works. Given a dataset, we first extend it, adding a weight field to every instance with a value of 1. We then enter a finite loop where in each interval, the algorithm creates a model from that dataset, then creates a batch prediction using that model over the entire training set, including all of the features. And then we're going to use that batch prediction, which now has all the features of the dataset, plus a known outcome, plus the predicted outcome, to create a new source, which contains now all the features from this original dataset, but plus a predicted outcome. And then use that source to create a new dataset. And then we're going to use BigML's flatline feature to compute new weights by comparing the predicted value with the known value and adjusting the weights according to an algorithm whereby we multiply by 2 if the prediction was wrong and by 1/2 if the prediction was right. And in this new data set, we're also going to then remove the predict column. So when we come back around to this, we just have a data set with adjusted weights, and then we go through and model, batch predict, source, data set, reweight, and go around and around. So overall, the idea here is to increase the weight of each instance the model got wrong, and then train a new model that pays more attention to the mistakes. And then the final classifier will just be a simple ensemble of all of the models that we train. Now to demo this ToyBoost, we're actually going to use the letter recognition dataset from the UCI repository. This data contains 20,000 instances of various image properties for the letters A through Z, and the goal is to build a classifier which can predict the letter from these image properties. And let me pop over here and show you. So I've actually already split this data set into 2. One that's a test set and one's a training set with an 80% split. And so we'll train on obviously on the training set, and then we can do a quick evaluation at the end. So let's have a look at the code, and I'll just kind of walk you through how this works. So this first line here, we're just defining the location to the file, obviously. We've seen this before. We're importing the BigML module and instantiating a connection to our API. Then we're going to create what we're calling our original source using the file that I've specified up here above. And we're going to give it a name of Mr. Boost original source. And then we're going to ask the API to wait until that resource is done. Then we're going to use that original source to create a data set and call it original data set. And again, wait till it's done. Now, once we have a data set, we can actually look at the document that comes back from the create data set. And inside there's a key called object. And inside object, there is a field called objective field. And this is the default objective field that the dataset algorithm chooses. and this is typically the last valid column in the data set. And I've already changed the UCI data set so that the column we want to predict is the last column. So basically all I'm doing here is extracting the field ID for the objective by just taking the what the data set determined the objective field to be, which in this case is the last column, which is exactly what we want. And so that's an assumption of my algorithm. If you were going to make this a professional algorithm, you would have to account for that. Then we're going to create a data set. This time, instead of creating a data set from a source, we're actually going to create it from a data set, which you can do. This is how you do sampling, filtering, and field extensions using flatline, etc. And in this case, this is actually a call to extend this data set by adding a new field. In this case, the new field name will be called weight, and this is a little JSON expression for a flatline command. And basically, all we're doing here is we're saying if 1 equals 1, which is always going to be true, then the new field will have a value of 1. So I'm just adding a column of all 1s. And we're going to name this data set train 0 because this is where our iteration is actually going to begin. And then we'll save this, or we'll wait until it's done. And then to make sure we've got the current data set, we'll go ahead and fetch it. And now this next line here is sort of another little trick of the API. There is this fields method that you can, or fields object that you can import. And this is handy because it allows you to easily convert field IDs to field names and field names to field IDs. So as you might imagine in our data set, we've got field names, things like XY bar or something like that. And when we create a data set, BigML actually creates unique identifiers. You could theoretically have a data set that has 4 columns that all have the same name, and BigML is fine because it will just number those 0 through 3, and the name that you gave each column just becomes a parameter of that unique field identifier. But of course, this makes it somewhat more difficult when you want to interact with it, and I want to be able to call my field weight, but I don't know what the field ID is. So in this case, I'm just saving what the weight field ID is by looking up the field ID of the column that's called weight, which again is the column I added up here. And that way I can use this in my iteration. It's always going to be the same weight field ID because I'm keeping the data sets the same shape. And similarly, when we create the output from the batch prediction, we're going to include all of the features from the original data set plus the prediction column. So the prediction field ID is actually just going to be the ID of the weight field. So in this case, I'm actually taking the weight field ID and converting it to an integer and adding 1 because it's going to be the next column, and then reformatting this as a padded 6-digit hexadecimal number. So this is just actually a cheat. I know ahead of time the prediction field is going to be the weight field column ID plus 1. So at that point, we're ready to go into the actual loop. So we'll do this 10 times, and at the start, we'll make sure that the data set we want to train from is ready. And then we'll create our model here. So we can see we're giving it a name that increments each time in the loop. We're specifying, this time we're actually specifying the objective field. In this case, remember, we saved the objective field ID above, so we want to make sure we always use the same objective. We're going to exclude the weight field ID from the modeling algorithm. We don't want it to model off the weights. But we do want the modeling process to use the weight field in the learning algorithm. Then we'll wait for the modeling process to be done. Then we'll use that model here to create a batch prediction over the training set. And again, here are the options. We're going to give it a name that iterates with each loop. We're going to tell the batch prediction to include all fields in the output. We're going to ask the batch prediction to also include the header, which has the feature names. We don't want the confidence because that'll mess up our column counts. And we're going to make sure that the prediction column is named prediction so that we can compare it easily with a flatline expression later. And then we'll wait for that batch prediction to be done. And now here's kind of a little trick. So once you've created a batch prediction, what you actually get, one of the things that's available is a URL that you can use to download the output of the batch prediction as a CSV. And we can actually create, since we can create sources from a remote URL, And since a batch prediction download is just a URL, we can actually create a source from our batch prediction just by taking the location, which is sort of the canonical location. This has the complete URL to BigML.io in it. Adding the download feature, which this means rather than show the information in, say, for example, the dashboard of what the batch prediction looks like, we actually want to retrieve the batch prediction. And we can actually add the credentials to our source creation by treating the API object as a dictionary. And if we do that, you'll find that there's a parameter in there called auth, which actually has the username and API key in it. And so I've basically just constructed a URL which I can use from the batch prediction, which I can use to create the new source. And again, we'll give this a name that increments with each loop. Wait till the source is done. Now we need to create a result set. Now this is different than the training set because this actually has all of the features that we're interested in for training plus the predicted outcome. So we need to create a data set from that. Again, naming it to iterate and wait till it's done. And then here's our final magic step. We're going to create a new training set from the result set. So this is the data set that we created from the source from the batch prediction again. And this time we're creating a new field, or we're recreating the weight field. And here is the flatline expression that does what the algorithm I described, which here is if the objective field ID it has the same value as the prediction. So in other words, if the known value has the same is the same as the predicted value, then the weight field will be the last weight divided by 2. And if it's not equal, then the new weight will be the last weight, but multiplied by 2. This all but parameter. So again, the new weight is twice the old weight if the prediction was wrong, and half the weight if the prediction was right. So this parameter tells the dataset creation to include all of the fields except for the prediction field ID and the weight field ID. So that's the old weight and the prediction, because we don't want those in our new training set. And to then, of course, name this with the next iteration of the loop. And then we go back up to the top. We have our new training set, and the algorithm flows through 10 times. So let's go ahead and kick this off. And we can actually see it start in the interface. I'm using a different user, so let me log in as that user. So here we can see it's created the original source. Here's the original data set. And here's the training 0 set. And now remember, the only difference between the original data set and the first training set is that we've added this weight column, which you can see only has one value because it's 1 for every instance. And then we've used that data set to create model 0. And then we used that model to create a batch prediction called result 0. And here's that link where you can download this CSV, and you can see here there's the header. This is the original predicted column called letter. Here's the weight that we used, and here's the predicted value. That batch prediction is then used to create this source, which you can see all of the features, plus again the known feature that we're trying to predict, the weight that we used. This time, this first loop, it's of course all 1s, and here we can see what the predicted values were. So this one was correct, this one was wrong, this one was correct, etc. Then of course we use that source to create our first result set. Of course, the weight is all 1 for this, and here are our predicted values and known values. But then we apply our extension to create our first training set, or really our second training set, and now we should see adjusted weights. And indeed, here we have 12,593 instances that were classified correctly, so we've divided their weights in half. And here we have 3,407 instances that were classified incorrectly, and so we've doubled their weights, and then we repeat. So as you may recall, the final classifier that we're going to use is actually going to be an ensemble of all 10 of these models that we're creating. But we have a little bit of a problem in that, BigML doesn't currently allow us to create an ensemble from individual models through the API or the UI. That is a feature that is coming eventually, but is not available yet. And so how are we going to evaluate this ensemble? How are we going to put the 10 models together and do the evaluation? Well, I've created a script, which I'll show you now. Basically, we have, again, a very simple script. We're loading the test, or defining the location for the test file, instantiating a connection to the API, and then we're just going to go into this very simple loop where we're going to make an API list. And I'm cheating here because I'm using a separate user with a clean account. I'm just listing all of the models. By default, they'll be listed newest first, so I'm reversing it. So I have oldest first, which in this case would be the earliest model, if you will. And then I'm just constructing an array that's just the model IDs by looking at the resource for each object that comes back from the API list. And then I have a very simple loop here that takes each model ID and builds up an ensemble. So the first time through, we'll just have one model, then two models, then three models. And each time, I'm making sure that the last model on the list is done. And then I'm going to instantiate a local ensemble, the same way we did a local model in the Python example earlier, using all of the list. So for a local ensemble, you can just pass it a list of models, and it'll actually go and fetch all those models through the API and instantiate an ensemble in my local environment from those models. And once I've done that, I can actually read our test file using the CSV module. And then I can just very simply compare from each row in the test file the value of the letter column to the output of my local ensemble classifier, generate a prediction over the same row. And then I'm just going to make a simple count of how many errors, and then output the data as to how many errors and the percentage correct. So let's go ahead and run that. And I've tried to make it so it's okay to run even if the boosting algorithm is still running. So here we can see just fetching the first model, we had 947 errors with a percentage correct of 76. Adding the second model hasn't changed those statistics yet. But we're now fetching the first three models and building an ensemble. Now we can see a number of errors to 742. Percentage correct has risen to 81%. With four models, our errors are falling and our percentage correct is now up to 85. And I believe if we let this run all the way to 10, it gets as high as 93.5 or 94%. All right, so we've seen how the BigML API makes machine learning as easy as a few API calls. And we've seen how the Python bindings abstract those calls to an even more powerful level. Now, BigMLer is one more layer of abstraction on top of the Python bindings and offers a high-level command line tool for machine learning. In a single command, BigMLer can upload a source, create a dataset, train a model, and even evaluate the model, among other things. When uploading a source, BigMLer makes correcting field types easy by allowing specification using a flat file containing the desired types, for example. BigMLer can also create predictions remotely. It can create predictions locally. It even works with our predict server, which is an Amazon machine image that you can deploy and use to do very fast predictions. And BigMLer even includes a few special features which are not available in our API or our UI, including cross-validation and multi-label predictions, which we have blog posts on both of those topics. But I want to show just a very quick demonstration of BigMLer. I see the time is a little short, so let me go ahead and pull that up. We'll just do one quick example. We'll repeat the same train or upload or create a source from S3, create a data set, train a model. So we'll do that. First, we'll set up our environment. So we need a username and an API key and set up our authentication. And now we'll just make a call to the BigMLer script. We'll pass it the train parameter. We'll give it a location, which in this case is an S3 location, but of course could be a source identifier in the BigML tradition of source/ID. And that's actually all we need. Just with that, BigMLer will automatically create a source from that remote, automatically create a data set, and then model that data set. And we can actually see that again in the dashboard. Here's the source that BigMLer created. Here's the data set, and again, here's the model. Now there's quite a lot that can be done with BigMLer. I barely scratched the surface, but and we actually have customers that are doing their complete integration using BigMLer specifically for the cross-validation. Anyways, there's enough features in BigMLer that could easily be the topic of a future webinar. But as you can see, BigML's API is not a bolted-on afterthought. We've worked hard to define a feature-rich machine learning API that just happens to have an easy-to-use UI on top. And we will continue to expand the capability of the BigML API, making a wide variety of scalable machine learning algorithms available to integrate easily into your application.